SwayamPrabha. Digital India. Educated India.
Okay, so a random variable is a variable whose value is an outcome of a random phenomenon. See, the outcomes are unpredictable. Okay, so whether you'll get a head or tail is unpredictable. But if you do it over 100 times, if it is an unbiased coin, so approximately 50 times you should get head, 50 times you should get tail. It may be 49, 51, or at the max 52, 48, and all that, but it will be close to that 0.5. So that is a random phenomenon. Okay, so a random variable basically can be classified as two types. One is a discrete random variable. A discrete random variable is the outcome can be only head or tail. Okay, so the outcome, but there could be some other random variable whose outcome could be 0.12, 0.016, 0.004. It can be a real number, the outcome. Okay. See, for example, the number of rainy days in India, right? That's a discrete in a year. That is a discrete. That's a discrete random variable. But the probability of rainfall exceeding the monsoonal average, seasonal average rainfall exceeding the seasonal rainfall exceeding the climatological average. That probability is basically a continuous random variable. Okay, so discrete is it can x of n. So we'll get the distinction of capital X and small a little later on. Assumes only discrete values n equal to 1, 2, 3, blah 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 up to n. Continuous can assume all values in an interval of real numbers. Okay, so now the next thing comes probability distributions. See, the definition of a probability distribution is tricky, and a good workable definition is assignment of probabilities. The assignment of the probability to the value of the random variable gives the probability distribution of x. Okay, so watch this statement very carefully. It's a loaded statement. Assignment of probabilities to the values of the random variable. Okay, that gives the probability the distribution function, or it could be just a number. The probability of getting a head is half. Okay, is that okay? So it is the assignment of a probability. What is the probable value of the random variable? That is the probability distribution. Okay, the probability distribution is usually denoted by f of x in probability theory, in the subject of probability. Okay, so please note there is a difference between probability and statistics. Okay, you start with a random variable and the probability, this thing, blah 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 blah, all that, and you work out all the distributions, theorems. This is generally probability. But if you say there are 50 students in a class, find out the average height of the student, what is the standard deviation? That is statistics. Okay, you may apply the laws of probability to data. Okay, and you may do statistics with that data, but basically probability is mostly about conjectures, theorems, theory, and all that. If you apply the laws of probability and analyze set of data and all that, this is called statistics. So usually the difference between probabilist and statistician is statisticians will work with data. Probabilists can end their career with just proving theorems, and what they require is only a paper and pencil. But a statistician will require a computer. He will require a program. And if you're a Bayesian, if you're doing inverse, you may require heavy computation. So without the computational power, a statistician cannot survive. Okay. A probabilist, if he's extremely good in mathematics, he can just keep on doing something, and the integral calculus, differential calculus, he can discrete maths, and he can proceed forward. Okay. So sigma n equal to 1 to infinity, f of x equal to 1, okay, f of xn, when x is discrete. So this becomes minus infinity. All real numbers means they can go from minus infinity to plus. F of x and dn, f of x dx. 1. When x is continuous. Is it okay? Okay. So the sigma of all of f of x will be 1, or the integral will be equal to 1. Okay. Now next we go to an important concept called expected value. It's also called expectation. Okay. So E of x f of xn when x is discrete. Okay. So if x is the random variable and fx is the probability distribution, so it is a product of x into f of x dx, and you integrate it from minus infinity to plus infinity. So some people also call it as the first moment, moment. The first moment of the probability function, of probability distribution function, is called the expectation. In fact, the second moment is nothing but the variance. Okay. So this integral could be replaced with a summation if x is discrete. Is it okay? And for the simple case, when f of xn equal to 1 by n, you know that this expectation will be nothing but the arithmetic mean. Okay. So what is that? E of x is nothing but weighted mean of all possible values of x multiplied with the corresponding weights. So please note, I am using a fine difference between x and x. X is the general random variable. It's like God. There is x. This x. So that x can take the form of small x1, small x2, small x3, small x4, and so on. So if I expand it, if I put it as an integral and all that, I will use small x. But generally, a random variable means I will put capital X. Okay, this is what we do in maths. Okay, so that x includes everything. The capital X is like the superset. It is like the God. Okay, it is a general random variable. Okay, so weighted mean of all possible values of x multiplied by the weighted mean of all possible values of x multiplied by its corresponding weight, and this is the weighted mean. If f of x equal to 1 by n, then okay, this just okay. So this you can put it within brackets. Okay, so if the heights of 50 students in the class, that n equal to 50, so sigma I equal to 1 to 50 of yi or hi, where h is the height, divided by 50 will give you the mean. That is the expected value of e of h, height. Then the e of h, that height, that h is nothing but your random variable x, capital X. But this x1, x2, x3, x4, x5, x6, they are all the students in the class. These are all the various entries. Is it okay? So these are the values. So and the height which they take. So e of, you don't say e of small x. You say e of capital X. That capital X is basically your random variable. That random variable in the simple height problem in the class is the height. But that random variable takes its avatar in the form of 50 students who are having the distribution. There are 50 heights. Then you do all this masala and finally you say there is an expected height. That expected E of capital H. That E of capital H is the E of capital X. But inside will be small x. Is that okay? Inside that expression. Please note this difference. Okay. So when I am in flow, when I make some small unknowingly, if I make some errors, if I put capital X instead of small x and small x in terms of instead of capital X, you take down the notes, go back in the evening and revise, and then wherever, if there are a couple of places where I have made that error inadvertently, change it. Basic fundage, x is the superset, capital X encompasses everything, x is the individuality. Okay, x1, x2, x3, x4, and so on. Is it okay? Now this is fine. So usually the expected value is simply referred to as the mean of the distribution. It should actually be the weighted mean of the distribution. But if f of x equal to 1 by n, then you can say that it is an arithmetic mean. So mean, so if somebody asks you mean, you have to be very clear what mean you should say. Arithmetic mean is the simplest mean which is possible. Is that okay? Usually, so basically you're suppose quiz 1 20%, quiz 2 20%, and and some is 60%, for example. I'm not saying in this course. Okay. Suppose all the quizzes are set for 50 marks paper. You cannot say if you add quiz 1 plus quiz 2 plus n sum divided by 3, then you are in trouble. Because in that case, you assume that all the fellows have an equal weight, but that is not your mean performance. Okay, that is not the way to calculate an average mark. The average marks will be marks obtained in quiz 1. Okay, convert it to 100 and multiply it by 0.2. Marks obtained in quiz 2, converted into 100, multiplied by 0.2. But marks obtained in the end sum, converted to 100, multiplied by 0.6. Then you get a total performance. Okay, that is the weighted mean or whatever, weighted sum, whatever. All right. So Then we can do it for all the students, and then we can take sigma of y divided by n, that will give the average marks, and then we can work out the standard deviation, so on and so forth. All right. So there is a difference between weighted mean and mean. Usually expected value is referred to as mean. Don't say it is a mean of small x. It is a mean of that x. X is the royal x. It is the random variable. It is the phenomenon which you are trying to investigate. All that is construct. All these definitions will help you to, are basically constructs. They're all props. They're all some devices or some constructs which help you to understand the subject. Is that okay? They should be our slave. We should not become the slave. So it's not basically, it is somebody imagined that it is something called x, but finally it is a real quantity. What is that? The heights of 50 people. The average height is something, nobody can be the average height. Nobody may be the average height. All people may have some difference with respect to the average and so on. So the average height may never exist. The average height may never exist. What is reality is the 50 heights. But with the average height, I can say a lot about the statistics. I can talk about this thing. I can do so much of this thing, mental gymnastics. Number one, I can do mental gymnastics. Second, I can also solve some meaningful problems. That is the way I can understand this, because I want to quantify my errors. I want to quantify the confidence intervals with which I am able to predict and so on. So please note that average height is not a reality. 50 heights in the class are a reality. Standard deviation is not a reality. Standard deviation is somebody goes, our forefathers defined it. That's all. But it is quite different from the measurement of the height itself. 50 heights are hard data. And whatever you are doing subsequently, whatever we are doing today, it is our way of approaching truth. We feel that we can understand it. But this limitation often you forget, because it is ingrained from high school. Then this is this ultimate, this object, this ultimate. This is one way of looking at it. That is, somebody thought that let us call it as a random variable, let us call it distribution, let it be discrete, let it be continuous, let there be some integral calculus, let it vary from minus infinity to plus infinity. Of course, in the case of height, it cannot go from minus infinity to plus infinity. Okay, so is that okay? So there are but basically, the idea of approaching a subject like this, because you want some universality, you want a set of mantras or sutras, you want a set of mathematical principles by which you can understand many problems. Okay, it has helped man solve many problems. So, but please note that whenever you go deep into the subject, you should also understand the limitations of that subject. All right. Now, expected value of a function. Expected value of a function of g of x is expectation of g of x okay, equals g of xn into f of xn. So here I think we should use x. Okay, I hope so. When x is continuous. Don't worry too much about the nomenclature. So long as you understand what is going on, it should be fine. What are the equation numbers for these two? Can you tell me? Am I audible?
Sir, 5 and 6.
Okay. Hey, please alert me if I am not audible. because this is not fully charged. I'm going to pick up some drop chalk piece in the ground. Okay. Let's put it in the dustbin. All right. Okay. So far so good. 5 and 6. Now variance. Of course, variance is again random variable is x. The variance is denoted by sigma square. Of course, I don't know historically who proposed it as sigma square. Why the sigma square was? I think maybe the sigma is always used as the sum, and then so the sum of the square of a value minus the average whole square. That's how then finally, if this is the sigma, this is the Greek sigma for capital. This is the Greek sigma for the lowercase. I think finally this came like this. I don't know. Otherwise, I have to go and check, because they should have been the first guy. Okay, Gauss and company, Gauss and co-workers, Laplace. One of these guys must have done this. Okay, so variance of a random variable is given as sigma square. Okay, where mu is very frequently. I'm very fond of this. I think many statisticians are fond of this. Mu is generally used for the mean. Mu is a very good. I don't know why it came. Both are m. I don't know because of that. Mu equal to e of x. Okay. 8. Okay. So sigma square equal to e of x square. Okay. So this can be written as sigma square equal to e of x. Am I audible? Fine. So just do a thumbs up.
Yes, sir.
Okay. Now so I get some 3 minutes. I'll go and charge this again. So prove this. Just prove this. Okay. So a proof of equation 9. Okay. E of x minus mu whole square equal to minus infinity x minus mu whole square f of x dx. And e of x minus mu whole square integral minus infinity to infinity x square f of x dx minus 2x mu f of x dx plus mu square. Agreed? Okay. Therefore, what is this? X squared f of x of d of integral minus infinity to plus infinity x squared f of x dx is nothing but d of x squared minus mu is a constant. Mu can be taken outside, 2 can be taken outside. X of f of x dx integral minus infinity to plus infinity is basically minus 2 mu e of x. Okay. Plus mu squared into mu is a constant. Mu squared into integral minus infinity to plus infinity f of x dx equal to 1. That was one of the first equations I wrote in today's board, in today's class on the blackboard. Is it? That's okay. So you just check it. Mu is a constant, can be taken out. Integral minus infinity to plus infinity f of x dx is nothing but mu square. But the sheer beauty of the matter is e of x is nothing but mu. The beauty of the matter is e of x is mu. Okay. So this is nothing but plus mu square minus 2 mu square. Nothing but minus mu square. So simply you can sum the x, you can sum all the x's, square them and get the mean. That is e of x squared. Take the mean and square it, get the difference. So this is also another way of calculating sigma square. Of course, what we did in the class in the first problem was we just took x minus x bar, y minus y bar, t minus t bar whole square, sigma, and then this was basically used to find that st minus sr by st and so on. So this is good. Okay, now this is how much? This is 12. So as we read, proved. That's it. We proved it.
Sir, I have one small doubt, sir. Sir, in the discrete well, if x is discrete, if we take this form, then we get variance is equal to x minus mu by whole square by n. We will get no, sir. If we take this one,
I don't quite get what you're saying. It looks like you're talking from the well. You're saying that I could figure out that there is some problem if you do
you
it.
said variance calculation. Once you said we have to take n minus 1 in the denominator.
No. That is for the standard deviation of the estimate.
Okay, this one is.
This is the variance in the data.
Okay, sir. Both are both different, sir.
No. That is sigma square of the estimate. I am taking the estimate. No, this is just the data.
Okay.
I am doing an estimation. I am going further. I taught you something advanced. When you put y equal to ax plus b, there is a proposal already. Is that okay?
Okay, sir.
That is some advance. You are using a predictor. Okay, that is some advance. That is an inverse problem. So here we are just saying there is a data, there is a probability. We are still sticking to basic probability and statistics. Those degrees of freedom and all that will come when you are doing that estimation and all that. Is that okay? All right. Okay. All right. But even then, if you're saying that you have n data, you're already using 1 degree of freedom is lost in calculating the parameter. If that is what you treat it as a parameter, then it will be n minus 1. So this universal confusion which exists from time immemorial. Okay, n by n minus 1. So I will answer like an engineer. When I have 100 temperature points, I'm trying to get some average. Whether you use 100 or 99, it will not matter at all. Mathematics, you just leave it. It's just a definition. It's just a definition divided by n minus 1. Let us not lose sleep over it. Okay. So if I'm doing a regression, standard error of the estimate will be all this divided by n minus 1, because 1 degree of freedom is already lost. For example, why I'm doing that n minus 1 is, if there is only one data point and the standard deviation is meaningless to define, because that is the point, that is the mean, and the variance will be 0. So it starts from 2. Somebody makes a mistake of dividing it by 0 and all that, and so that is the whole thing. So that is why all that is coming. So I mean, somebody, the caution is, if you put n minus 1, the caution is don't apply it for n equal to 1, because there will be some purists, no? Although, since you're all so much of mathematics, JE, because you think that the truth lies in the form, truth lies in the calculus, truth lies, if something is in the textbook, that is the truth, because you are so bound by that. You don't even ask what, because you have not even, we have been brought up like that. We never ask that question, what if this could be wrong? I mean, so that is there, that we have to master it, we have to get past the others, we have to clear GAE, because the goal was that we never really went deep and then found out why it was proposed like this. Okay, I have no problem with n or n minus 1, but I don't want you to calculate it for n equal to 1. Is that okay? Is it a fair answer?
Okay, sir.
Don't try to lose sleep over this. These are all definitions. Okay, I mean, so these things should help us to proceed further. They should not make us get stuck in one place. That's what I'm saying. So if Suraj is taking 100 temperatures, 80 temperatures, I mean, even if you write a journal paper with n or n minus 1, the reviewer will not really question. Okay, but if you are doing an estimate, better to use that n minus 1 for 1 degree of freedom, n minus 2 for 2 degrees of freedom, and so on. All right. Okay.
Hello,
Now
sir.
this is fine.
So one
So
small doubt.
think of, so this is called standard deviation, sigma. Okay. So this is standard deviation in the data. Covariance. That's what Anand Kishore is obsessed with, the covariance. Huh? Covariance of the covariance of two variables is a measure of linear dependence between them. Okay, the covariance is an important quantity. Okay, the covariance is an important quantity which we also use in inverse heat transfer. Okay, if you're correlating several parameters, okay, the covariance should be zero if you're looking at correlating Nusselt number or heat transfer coefficient as a function of several parameters. However, there should be a positive covariance between the heat transfer coefficient and the Reynolds number. Are you getting the point? But if there is a, how do I say this? Let me think. Okay, Nusselt number equal to A into Reynolds number to the power of B Prandtl to the power of C, let us say. Okay, all of your heat transfer students, you've studied heat transfer. The Nusselt number is a dimensionless heat transfer coefficient. So let's say for a pipe, it is Hd by K. Anand Kishore, are you there, Anand?
Yes, sir, I am there, sir.
Anand Kishore.
Yes, sir, I am there, sir.
Yeah. So the whole funda is the covariance of the Nusselt number and Prandtl number must not be 0. Otherwise, there is no relationship between that. But the covariance, Anand. The covariance of the Reynolds number and the Prandtl number must be 0, Anand. If the covariance of the Reynolds number and the Prandtl number is some finite quantity, we are in deep trouble. That means if you know the Reynolds number, you can predict the Prandtl number, which means they are not independent quantities. So what is independent, what is dependent is fundamental in the analysis, in modeling, analysis, simulation, optimization, inverse and whatever. Therefore, covariance analysis is a wonderful tool, particularly when some of you are so hung up on data science, big data, data analytics. What is data science? See, who are these data science people? See, I'm also reading books on big data. Okay. Hey, some of you should show thumbs up, man. See, I have also joined the bandwagon. I'm also reading books on big data. Okay. All right. Everybody says big data. Okay. Now, in the heat transfer, sir, it is obvious, sir. You will say, Anand, you will say, sir, it is obvious, sir. There is no connection between Reynolds number and Prandtl. But I am an editor of an important journal in heat transfer. I'm sitting there every day after I look at papers. Okay, every day I have to do that. Just like it's like a tapas. Just like morning you get up, do puja, take bath. Because there are so many journal papers, so every day I have to allot some time, either in the morning or evening somewhere. Otherwise, it will get piled up in my inbox. Now, somebody is so enamored by his or her calculation, and then he wants to present it in a correlation. Correlation is a fancy. Correlation is a fancy for all heat transfer researchers, because somebody puts all the quantities on the right hand side, he gets a Nusselt number. Once he gets a Nusselt number, he gets a heat transfer coefficient. He can design his heat exchanger. He can make a heat exchanger, boiler, evaporator, all that. He can make industrial equipment. So the key to unlock this would be the knowledge, the final culmination or the summum bonum. The summum bonum or the climax of the heat transfer, convective heat transfer study would invariably be to predict the Nusselt number in the form of a correlation. But sometimes people have these correlations with multiple parameters, and often I ask them the question. Some reviewers also ask them the question: did you establish that all the parameters are independent? What are the fundamental independent parameters which govern the problem? Or is it like I hate to use this word, but I hope you understand. We call it as incest. INCEST. Is that okay? That means some close relatives should not marry each other. That is what is human. So this word incest can also be used in scientific parlance. Incest means A is causing B, therefore B is causing A. Therefore, if you go, where is your house? My house is next to Anand Kishore's house. Where is Anand Kishore's house? Anand Kishore's house is next to Balaji's house. Where you are not proceeding further, right? So like that, it will get into a circular argument. Reynolds number is dependent on Prandtl number is dependent on Reynolds number. Which of the two is independent? I mean, which do you want to use? But in your experiments, you are generating a lot of data. Okay. So, in order to arrive at what is the minimum, so sometimes you have to do what is called, principal component analysis. You can do principal component analysis, and you can just take a weighted linear mean of all the variables, weighted average of the variables, and then propose it as a component 1, component 2, component 3. So you are still in early days when you are dealing with a lot of experimental data, a lot of data available from stock market, whatever, regarding depending on the field where you are going to work, you will be confronted with a lot of data. So you have to first sift out the noise from the data, and then you want to make sense of the data. Therefore, this covariance analysis is a very powerful tool for you to do this. Anand, did I answer your question?
Yes, sir.
Okay, so we go further. So then, where is the hope, sir? Where is the hope? So if you ask me where is the hope in a subject like heat transfer, to find out the independent set of parameters. In heat transfer, I will say there are two main approaches. You take the governing equations and keep on non-dimensionalizing them. U velocity is equal to U by U infinity, V equal to V by V infinity. Temperature is normalized as T minus T cold by TH minus T cold, so that all the temperatures are between 0 and 1. All the velocities are between 0 and 1 and so on. Once you do that, the equation will present itself in a new avatar where it will give some key dimensionless groups. These are the dimensionless groups which really control the problem. With that, once you get a temperature gradient, Q equal to minus K dou T by dou X, thanks to our big boss, Fourier, and apply it at the wall, get the heat transfer rate, get the Q. Again, thanks to our friend Newton's law of cooling equal to HA delta T, get the H. Again, thanks due to Nusselt, HD by K equal to NU. Then again, thanks to Reynolds, velocity can be put in normalized form. Again, thanks to Prandtl, nu by alpha can be written as Prandtl number. So you can, with the help of all the previous scientists, your forefathers, you will package and present nicely a correlation or an equation which can be a predictor for the heat transfer coefficient occurring in the problem. But if you are predicting a correlation, the right hand side, are you sure? Are you sure that you have taken only those parameters which are independent? For that, if you have a lot of data, you have to do a covariance analysis. This is called a brute force approach. A Pakka scientist will take the governing equations and then non-dimensionalize them and figure out the independent parameters. An even better approach would be to use the Buckingham pi theorem and start with every quantity velocity m to the power of 0, l to the power of 0, t to the power of mlt. You know the basic U-dimensional analysis, regroup all the things and equate all the powers and exponents, and then finally come to the same conclusion of Reynolds number, Prandtl number, aspect ratio, whatever. So this is as far as heat transfer is concerned. If you're doing big data analysis in some other subject, first go into the subject. See last 100, 200 years, who are all the big bosses, big shots who have developed this subject. Absorb it and then do it. Instead of then, otherwise, what is the difference between you and just a computer science guy who just looks at data as it is just a data, it could be anything. But for you, there's a temperature, there's a heat transfer coefficient, there's a Prandtl number, Reynolds number, all these become like living commodities. I mean, they're living entities, they come to life. Then you're able to get an organic relationship in all this through your theory, through your empirical knowledge, through the hard work of Reynolds, all this Prandtl, all these people developed experiments, did experiments to develop theory and so on. So this is how science and technology has progressed. So do you think the whole science and technology all this can be just replaced by some neural network, deep learning, all that? How much can it learn? Can it replace the learning of millions of people, brilliant minds who can think differently? The data and your final data science can do only as good as the data. It cannot do anything. It cannot do anything new. It cannot do anything new. It cannot do anything disruptive. So it is an interpolator. It cannot tell you. But science always progresses from one disruption to another disruption. So this disruption, I bet, cannot come from data science. Data science can help you do things very efficiently. But the world is not dependent, that doesn't depend only on doing things efficiently. You have to do some things differently. Then the answer may lie somewhere. I don't know. The answer may lie somewhere in different fields. It is for the investigators to find out. All right. So I rest my case. So I will charge my stuff.